Good afternoon. Welcome to Advanced Placement Statistics. My name is Mr. Royce. I'm going to be taking on the role of instructor for this afternoon. Let's begin, shall we? Let's pick up where we left off on the notes from Friday. We are learning chapter 26, the chi-square distribution, concurring counts, and hopefully you remember the Titanic problem in which we were trying to calculate the chi-squared test statistic using A, B, 80, 56, 24, CD, donate your car today, 8, 2. And which one was chi-squared? Where does it go in the jingle? C. It's C. It's also D. But we did the C portion. So that's where we're going to pick up. Today we finished the Titanic problem. It's chi-squared, not chi-squared. And here's what our conclusions were. Actually, it looks like we didn't, is it true that we didn't fill in since the conditions are satisfied? Yeah, we forgot to say since the conditions are satisfied. And why don't we go dual user mode here. Thank you. All done? Put it on my desk? Yeah. Thank you. Appreciate it. So, since the conditions are satisfied, and notice that when I go into dual user mode here, it tends to work a little bit better. There we go. Okay. So, since the conditions are satisfied, we will use a chi-square model with, and we show our work, although this kind of looks familiar. We did fill in this part, didn't we? Yeah, because I must have fast forwarded to the last page of the handout, which has these filled in. So, yeah, now I remember we filled that in. We filled in this. Would you please draw a picture of the chi-square distribution labeled chi-square with a subscript of 3? It's a chi-square distribution. The 3 subscript indicates we have 3 degrees of freedom. And the chi-square test statistic took on a value of 187.7932, shade to the right. Notice there's no observed value. We go straight to the test statistic. There are actually 8 observed values, but only 1 test statistic. And the p-value was 1.829 times 10 to the negative 40th. So the probability that we observe a test statistic as extreme as 187.7932, or more extreme than that due to chance, is very low, 1.8 times 10 to the negative 40th. Okay. So, that was the Titanic problem. And I did put an interpretation of the p-value right here, in case they didn't ask for an interpretation of the p-value, but its interpretation is that the probability is 1.8 times 10 to the negative 40th that you observe a chi-square test statistic of that or greater due to natural sampling variation alone. And again, I'm crossing out natural sampling variation because we did not do any sampling. We didn't take a random sample of people on the Titanic and check to ask them, did you survive? Instead, it was just due to chance. So it could be that we could pick a sunken ship at random. We could randomly select a ship that went down, but still, it's just, that's not the basic idea that we're looking at. So sampling is not involved here. We're just trying to figure out whether survival is independent of class. And notice that that's the null hypothesis is what comes after the word given. It's time to get on to our next example. So we have problem 1 Notice we just finished problem 23. Problem 23 was the Titanic problem. That was a tough one. That puts it all together. Now we're going to go and look at the individual pieces. For each of the following situations, state whether you'd use a chi-squared goodness of fit test, chi-squared test of homogeneity, chi-squared test of independence, or some other statistical test. Okay. Now, we should look at the AB80 chart. Pull out your master copy of the AB80 chart. I happen to have mine right here, and notice that there are 3 chi-squared tests. 2 of them are stat test C, and one of them, the chi-squared test for goodness of fit, is stat test D. Now, just a heads up so that you understand when to use stat test C and when to use stat test D. Stat test C is used when you are given a two-way table. And mathematically, chi-squared tests for independence and homogeneity are identical. But you know you're going to be using stat test D when you're given is not a two-way table, but just a single list of numbers. Chi-squared test for goodness of fit is going to be a single list with n numbers. And notice how uncomplicated the degrees of freedom formula is. When you have it's just n minus 1. It's just the number of numbers in the list minus 1. So this is actually the less complicated of the two. But when you have a two-way table, the degrees of freedom formula is R minus 1, C minus 1. Now, we have not yet filled in the D row yet, have we? So I need to zoom in on that just a little bit. So the chi-squared test for goodness of fit, which is row 6, has the same formula for chi-squared. To calculate that test statistic, you still take the observed minus expected values, square those deviations, divide by the expected values, and for all cells, well, it's just a one-column. It's not a two-way table, it's a one-way table. It's just a list of numbers. So the number of numbers in the list minus 1 is all you need. It's called the chi-squared test for goodness of fit. What are the conditions for it? Well, those are on the far left. And notice the conditions are the same. It's counted data condition. We need the independence assumption to be justified by either randomization condition or representative sample, and the sample size assumption to be justified by the expected cell frequency condition. And that's satisfied if every expected cell frequency value is greater than 5. So those are just copied down from above. So wow, we filled in everything on the AB80 chart except for row 8, and row 8 starts tomorrow because we're finishing chapter 26 today. Chapter 27 is tomorrow, review on Thursday, test on Friday. Might be a little bit of teaching in chapter 27 on Thursday, but yeah. This is wrapping right up, coming toward the end. So back to this guy right here. Okay, so what's the basic idea behind a chi-squared test of homogeneity? We've talked about chi-squared tests of independence really since we've been testing independence since Unit 1. I mean, that was our opening example for the course. So you're really familiar with what the idea of independence is. But what would a chi-squared test for homogeneity look like? Just to give you a big picture here, suppose we had 2 ships sinking, God forbid. And suppose we had the Titanic, it sinks, okay? And then another ship, we'll say, should we say the Carpathia, the rescue? No, you don't get the rescue ship also sinking. I mean, it's one thing to have a sad story, but it's another thing to have a ridiculously depressing story. So instead of the Carpathia, we'll just say that just imagine that they did decide to build the Gigantic 3 years later, and then it sank. Gigantic. Okay, so the Titanic sinks in 1912. imagine the gigantic sank in the year 1915. And then what we can do is look for two distributions here. We can look at first class. This is going to be fatalities. And we'll just look at them, how about in terms of just percentages, second, third, crew. Actually, let's look at survival. Let's try. Since it's two ships sinking, let's look on the bright side. In fact, we'll look at percent survival. Okay. We could say, just in terms of raw numbers, just imagine there are 1,000 people on each ship. And so we could say also that there were, just to make the numbers nice, we could say that there's 250 in each, 250 people in each class. So let's say that we had, well, you know what? I am going to harvest the numbers from the Titanic example because mathematically it's the same. Just imagine that these same numbers are representing a different reality. Imagine that this is these are the alive counts for one ship, and these are the alive counts for a second ship. And we want to see if there's a difference in survival rates. And so the word homogeneous comes up to, it brings up the idea of same. Same. Are the distributions the same, or are they different? Are the survival rates the same or different? No. So that's how you can tell that you're doing a chi-square test for homogeneity, is it'll be like a situation where two different ships are sinking and you're comparing the rates for the two different ships. And I just want to show you the first actual example of that, because that's something that's actually really different than anything we've seen before. The first time that we actually see that in the examples here is part C. So let's just take a look at part C. Because it's your first example of a chi-square test for homogeneity. Okay? So, part C says the academic research office at a large community college wants to see whether the distribution of courses chosen, humanities, social science, or science, is different. Is it the same or different? They're not asking about independence. They're asking about same, homogeneous, or not the same, different, not homogeneous. So, oh, I see what you're doing. Trying to get a head start on part B. Okay, so we have two samples, residential, non-residential, and one variable course. So, just want to show you how this could be set up in a two-way table. And it looks like it could be a Titanic problem where you're checking for independence, but if you read carefully, realize it can't be that. So we have, so instead of alive and dead, we have residential students and non-residential. And it looks like the students can sign up for courses in the humanities, the social sciences, or a science course. So there's three types of courses they can sign up for. Now, suppose for the 100 residential students, or let's say 100 courses are taken among the residential students, and the courses they took were, the residential students signed up for 30 humanities courses, 60 social science courses, and 10 science courses, okay? So, how about the non-residential students? And they don't have to sign up for the same number of courses. They could sign up for a different number of courses. They could sign up for so far I've got 30%, 60%, 10%, and that's out of a total of 100 students, or 100 courses signed up. We don't know how many students, we just know number of courses. Suppose there's 200 courses taken by the non-residential students, but I'm going to make it so it's a little bit off. So instead of 60, I'll make it 62. For the social science courses, instead of 120, I'm going to go 110. Okay. And the next one's determined. I don't have any, I'm out of degrees of freedom here. So 172, so this has to be 28 for that to add up to 200. Okay, so mathematically, it looks like it could be a Titanic problem, where we've got, instead of residential, non-residential, we have alive and dead. So this is all one group of people, and there's 3 categories on this categorical variable, and we have 2 categories on this other categorical variable. So mathematically, it looks like it could be alive and dead for first class, second class, and crew. But we don't call it a chi-squared test for independence because we don't have one group with 2 categorical variables. Instead, we have 2 groups, and each group is distributed across only one categorical variable. So when you have 2 groups and 1 categorical variable, or in this case 2 samples, residential, non-residential, and therefore in your mind you're thinking this is like, it's like this is one ship that sank, and of the 100 people on board, we had how many first class survivors, or of all the survivors, how many first class, second class, and crew? And then here's a second ship that sank, and perhaps there's 200 survivors on this ship. How many were first class, second class, and crew? So as you can see, it's like having a situation where there's 2 sunken ships, and we want to compare the survival rates, or at least the number that survived in each one. Now, we're still going to do a stat test C, but when you see 2 samples and only 1 variable, in this case the only variable is the type of course, and we want to see if the distribution of courses is the same for the 2 groups, that's when you use chi-square test for homogeneity. But if you take a look at part B, actually let's go to part A. Here a brokerage firm wants to see whether the type of account the customer has, silver, gold, or platinum, affects the type of trades the customer makes by phone or on the internet. So when you think of that, that's a 2-way table. And we got silver, gold, platinum. What kind of trade do they trade by phone or on the internet? Come on, that's just one group of people. It's like one ship sinking. We've got 2 categorical variables. So when you have 1 sample and 2 categorical variables, then we want to see if account type, silver, gold, or platinum, is independent of trade type, phone or on the internet. That's your classic chi-square test for independence. So when you read a problem like that, you should think, oh, that's like the Titanic sinking. 1 ship, 2 categorical variables, let's run the chi-square test for independence. Now in part B, it says the brokerage firm also wants to know if the type of the account affects the size of the account in dollars. It performs a test to see if the mean size of the account is the same for the 3 account types. Well, come on. We're no longer talking about categorical variables. We're talking about quantitative variables. And we don't even have counts. We have things that can be measured in decimals. So it's neither chi-squared test for independence, nor homogeneity, nor goodness of fit. This is just something else. So that's, at this point in the course, when you have so many different tests to choose from, it's really important that you think through what are the conditions for using a particular test. So that wraps up page 3 of this handout. Let's pause here. Any questions on how to decide whether or not you're dealing with a chi-squared test for independence or a chi-squared test for homogeneity? We haven't looked at goodness of fit yet, so we still have to get a chi-squared test for goodness of fit. Yeah, question?
So really we're only looking at like if there was one sample taken or two samples taken?
Yeah,
Is that
I mean,
the
if it's
only
one
really
sample,
distinguishing?
well, oh, but we haven't looked at the chi-square test for goodness of fit yet. So right now, what we're looking at is if you have one sample and two categorical variables, and that's chi-square test for independence. Two samples with one categorical variable is chi-square test for homogeneity. Now let's take a look at what happens with what are the conditions for a chi-squared test for goodness of fit. Okay, so, and that's what problem 3 is all about. So in problem 3, after getting trounced by your little brother in a children's game, you suspect that the die that he gave you to roll may be unfair. It certainly can't be that your brother is better than you in this particular game. You've got to be able to blame it on something else, because you're not willing to accept the hypothesis that your little brother is better than you at anything. So, so you're checking to see if the dice is fair, because you suspect it's not fair. And so the counts on the die, when you roll it 60 times, you get 11 ones, 7 twos, and it's a little bit light. I want to make sure I'm reading that correctly. Is that 9 threes? 15 fours, 12 fives, and 6 sixes. Now, notice that that when you roll a die 60 times, you would expect 1 out of 6 times to be a 1. So all of these have expected values of 10. So the chi-squared test for goodness of fit compares an observed distribution to an expected distribution. And notice that it's really just one list of numbers. It's not a two-way table, it's a one-way table. We're going to insert the one-way table into list 1. I'm going to clear out list 1. I'd like you to do the same. Put the observed values into list 1 like this. Let's go 11, enter, 7, enter, 9, 15, 12, and 6. Those are the observed values. This is a one-way table. We're just going to compare this one-way table. So there it is, Caleb. That's how you know it's going to be a chi-squared test for goodness of fit, is if you just get a one-way table. Now, when you compare that to the expected values, all of which happen to be 10 in this case. They're not always going to be the same number. The point is you have to think about what are the expected values. And we've got them right there. Now, since this is our first example of chi-squared test for goodness of fit, and that's D in the jingle, AB 805624 CD, let's run a stat test D. So we go to stat test alpha D. The observed frequencies are in list 1. We've already put the expected frequencies. It's not like a chi-squared test for independence. When you run a stat test C, the calculator will calculate the expected values for you and put them into matrix B. But for chi-squared test for goodness of fit, you have to do the thinking and you have to manually enter the expected values into list 2. Now what it's doing is observed minus expected squared over expected. It's adding them all up to get a chi-squared value. And CNTRB stands for contribution. It's basically a contributed value. This is basically the value of observed minus expected squared over expected for the first cell. You can probably do that in your head. Remember, it was 11 minus 10 is 1, squared is 1, divided by expected, so that's 1/10. So the first contribution to chi-squared is 0.1. Let's do the second one in our heads. What was it? It was 7 minus 10 is -3. -3 squared is 9. 9 divided by 10 is 0.9. So do you see how it's calculating these individual? There's a total of 6 contributions to the chi-squared test statistic. This is just showing you what the individual ones. But the chi-squared value is 5.6. Yes, question?
So the degrees of freedom is 5 because you have 5 faces?
No, it's n minus 1. So it's the number of faces is 6 minus 1.
Why isn't it 60 minus 1?
Oh, because it's the number of cells. So it's basically 1, 2, 3, 4, 5, 6. I mean, we could roll the dice 600 times. And by the way, that's most common error made with chi-square test for goodness of fit is the degrees of freedom. People end up using, the number of tosses. Yeah, it's basically they'll total up. They think that n is 11 plus 7 plus 6 plus 15 plus 12 plus 6. But really, n is just the number of cells in the one-way table. So it's important to know what n means. So if the die is fair, how many times would you expect each face to show? We would expect 10 times. To see if these results are unusual, we use goodness. Okay, we're going to use goodness of fit. Why? Because it's a one-way table. The given information fits into a one-way table. We're comparing the distribution of a single variable to an expected distribution. So we're going to use a chi-square test for goodness of fit. The hypotheses are null hypothesis, the die is fair. Each side is equally likely to occur. Alternate hypothesis, the die is not fair. Each side is not equally likely. We have the conditions, the randomization condition, the expected cell frequency condition. Notice that the expected cells, since all 6 of these 10s, these green 10s, are greater than 5, we've satisfied the expected cell frequency condition. Okay? Now, the counted data condition, we're good on that. How many degrees of freedom? It's 6 minus 1 is 5. By the way, you can calculate chi-squared by hand because observed minus expected is 1. So observed minus expected is 1, square it to get 1. And 1 divided by 10 is 0.1. Do the rest of them by hand. Observed minus expected, 3. Square it, and then divide by 10. These are the values given to you by stat test D on the calculator. 2 squared is 4.4, and -4 squared is 16, 1.6. So notice when you add those up, you get the test statistic, which was given to you automatically on the calculator running a stat test C. So find the chi-squared value. We found it by hand. It's 5.6. And as I indicated on Friday, there is a chi-squared CDF. In case you don't, suppose you forget the jingle on the exam. It's like, and you don't know to press stat test D. You could just use 5.6 as your test statistic, go to your distribution menu, and pick up chi-squared CDF, which is item 8. So chi-squared CDF of 5.6, 999, 5 degrees of freedom, not 59 degrees of freedom, gives you the same p-value as stat test D. With those numbers, let's confirm it's the same thing. Yeah, it's 0.347 and 0.347. So you might want to make a note to yourself that the chi-squared CDF notation is chi-squared CDF of 5.6, 999, 5 gives you the 0.341. So in terms of the p-value, the probability is 0.3471 that we observe a chi-squared test statistic that's 5.6 or higher due to natural sampling variation alone in samples of the same size, given that the die is fair. So here we do talk about sampling because when you roll the die 60 times, that's a sample. Since the p-value of 0.3471 is high, we fail to reject the null hypothesis. There's insufficient evidence that the die is not fair. The third sentence would be, doesn't have to do with lying, has to do with rats. My little brother's better than I am. Number 5 is nuts. A company says its premium mixture of nuts contains 10% Brazil, 20% cashews. Okay, so we're looking at percentages. So we've got Brazil, cashews, almonds, hazelnuts, and peanuts. Okay? And so notice these are not numbers, but they're percentages. The distribution is 10% Brazil nuts, so 0.1, 0.2 cashews, 0.2 almonds, 0.1 hazelnuts, so that adds up to 20, 40, 60, so it must be 40% peanuts by process of elimination, by subtraction. Okay, now you find that there's 112 grams of Brazil nuts, so we're going to have to, upon weighing them, there's 112 of Brazil, 183 grams of cashews, 207 grams of almonds. This mixture contains, okay, 71 grams of hazelnuts, 446 grams of peanuts. You wonder whether your mix is significantly different from what the company advertises. By the way, you'd have to add all those up, find out percentage, but then the question is it percentage by, see, we got a fundamental problem here. The weights of the nuts are quantitative. I mean, what are we doing? Are we counting nuts like a body count after a ship sinks, or are we putting them on a scale? Once you put them on a scale, you realize, wait a second, this is counted data. This is not counted data, this is measured data. And so, chi-squared is out. However, what might you do instead of using the chi-square test? In order to use a chi-square test, you could count the number of each type of nut. However, it's not clear whether the company's claim was a percentage by number or a percentage by weight. Who knows? They didn't tell us, so we're stuck. But at least it gets us to wrestle with whether or not we have the green light to go and use a test. The next handout, paper notes, if you want them, part 2 of 3. Hold on, I'm trying to count part 2. This is one. Okay. So, what if I have part 3 of 3? Okay. So if you want part 2 of 3, just give your brain a break. Actually, try and get both these handouts, the part 2 and the part 3 of 3. They're right here. Well, one of each. You need them both. Okay. So we're going to part 2 of 3.
So tired. Oh my god. I guess you're also
Yeah.
Fortunately, part 2 of 3 is a short one. And we'll go. Let's go straight to page 2. Okay. Oh, good. Childbirth. So. Let's take a look at childbirth part 1. There's some concern that if a woman has an epidural to reduce pain during childbirth, the drug can get into the baby's bloodstream. We actually talk a lot about this at home because in our family, my wife and I gave birth. My wife gave birth to 3 children. The first 2 were with an epidural. I'm sorry, the first 2 were without an epidural. It wasn't until my daughter was born that she finally decided to use an epidural. And so instead of hours and hours of agony, it ended up being, 2 or 3 pushes. She's out. My wife was laughing the whole time. It's like, I don't know why she was laughing. Maybe it's because it's like, I can't believe how much this doesn't hurt with the epidural. And, but downside is that it could make the baby sleepier and less willing to breastfeed. So in December 2006, this is a thing. This is the International Breastfeeding Journal, published results of a study. I don't subscribe to this journal. Never read it, but apparently it's a thing. And researchers followed up on 1,178 births, noting whether the mother had an epidural. So that's one category, whether the baby was still nursing after 6 months. So what does this seem like? Does this seem like one sample with 2 variables, or does it seem like 2 samples with 1 variable? Basically, is this like the Titanic? Yeah, it does seem like it's like the Titanic. Instead of, we have a two-way table, it's just one sample, and we have two categorical variables. Did you get an epidural, yes or no? Is the baby breastfeeding after 6 months, yes or no? So we have the data, so let's go ahead and run a chi-squared test for independence, see whether they're independent. Go ahead and enter this 2x2 matrix into matrix A on your calculator. And then use matrix B to report out what those expected values are. So first enter the numbers into matrix A, run a chi-squared test for independence. Alrighty. Who has already looked at matrix B, and you can report to me what that value, or what those four values are going across the top? Just go to matrix B, it'll come right up on your screen. Bethany, do you have those?
For matrix B?
Yeah, just tell me what four numbers you got for matrix B, starting with row 1.
Oh, I didn't get there yet. Sorry.
Ryan, do you have them?
Sure, yeah, 236.7, 467.3, 159.3, and 314.7.
314.7. So you're thinking, are all those greater than 5? They all are greater than 5, but you have to write them down for matrix B. So there's two variables, breastfeeding, having an epidural. We're going to perform a chi-square test for independence. And again, all of those conditions have been satisfied for that. So the null hypothesis is that breastfeeding success is independent of having an epidural, and there's an association. The alternate hypothesis, notice how it's worded, is there is an association. You could say they're not independent, but another way of saying they're not independent is that there is an association between breastfeeding success and having an epidural. Now, when it comes to we're going to piggyback off of exercise 13, and how many degrees of freedom are there? So that's just reviewed. 2 minus 1 times 2 minus 1. There's 1 degree of freedom. And when you check the assumptions, they all work out. So going to the next page, we get, hopefully you've already put in those values. The calculator gave you the 5.9, and the conclusion for the test comes out to be that the p-value is very low, so we reject the null hypothesis. There's strong evidence of an association between having an epidural and subsequent success in breastfeeding. And so we're going to pick this up tomorrow, but the homework is due tomorrow. So you've got homework number 1. Bring that to class. You are dismissed.